Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration into one of the universe's most enigmatic phenomena, the question of whether black holes truly endure forever. We will be delving into the profound concept of Hawking radiation, a scientific marvel that suggests even these cosmic titans are not eternal. Prepare for a calm lecture, a quiet unveiling of how the very fabric of spacetime, intertwined with the strange rules of quantum mechanics, paints a picture of black holes not as inescapable prisons, but as entities that might, over unfathomable timescales, eventually fade away. This is an investigation into the universe's most profound secrets, revealed with a soothing touch, designed to quiet the mind and invite a sense of wonder. Let us begin our drift. Black holes are not eternal prisons. For a long time, the prevailing image of a black hole was that of an ultimate cosmic trap, a place from which nothing, not even light, could ever escape. This idea, rooted in Einstein's theory of general relativity, paints a picture of a singularity, an infinitely dense point at the center, surrounded by an event horizon, a boundary beyond which all paths lead inward, irrevocably. It's easy to imagine these celestial behemoths as eternal, unchanging entities, silently consuming everything that ventures too close forever. However, the universe, in its infinite wisdom and complexity, rarely offers such simple, static truths. As our understanding of physics has deepened, particularly through the groundbreaking work of Stephen Hawking, this seemingly immutable picture has begun to soften, revealing a more dynamic and ultimately, a more hopeful cosmic narrative. The concept that challenges this notion of eternal imprisonment comes from the realm of quantum mechanics, a field that governs the behavior of the universe at its smallest scales. While general relativity describes the grand architecture of spacetime and gravity, quantum mechanics introduces us to a universe that is inherently probabilistic, a place where energy and matter can behave in ways that seem counterintuitive to our everyday experience. It's at the very edge of the black hole, the event horizon, that these two profound theories, general relativity and quantum mechanics, are thought to meet and interact in the most fascinating ways. This interaction is the key to understanding that black holes, contrary to their fearsome reputation, are not destined for an eternal existence. Instead, they are subject to a slow, almost imperceptible process of change, a gradual release of energy that, over unfathomable timescales, can lead to their eventual demise. This realization shifts our perspective from one of absolute finality to one of cosmic impermanence, suggesting that even the most extreme objects in the universe are part of a grand, ongoing cycle of creation and dissolution, a testament to the universe's ceaseless evolution and transformation. It is this subtle yet profound insight that begins to dismantle the idea of black holes as eternal, inescapable prisons, opening the door to a deeper, more nuanced understanding of their nature and their place in the cosmic tapestry. The universe, it seems, always finds a way for even the most locked doors to eventually creak open. Even the deepest gravitational wells of the cosmos are not exempt from the universe's subtle, pervasive dance of energy. Hawking radiation is the universe's gentle whisper of evaporation. Imagine, for a moment, the most extreme objects we can conceive of in the cosmos, black holes. These are regions of spacetime where gravity is so intense that nothing, not even light, can escape once it has crossed a certain boundary, known as the event horizon. For a long time, they were thought to be eternal, a cosmic endpoint, a place from which no information or energy could ever return. But Stephen Hawking, through a profound synthesis of quantum mechanics and general relativity, revealed a breathtakingly different picture. He proposed that black holes are not entirely black, nor are they eternal. They are, in fact, slowly radiating energy into the universe, a process that, over immense timescales, leads to their eventual demise. This gentle, almost imperceptible emission is known as Hawking radiation. To understand this, we need to dip into the strange and wonderful world of quantum field theory, particularly the concept of the quantum vacuum. In classical physics, a vacuum is simply empty space. But in quantum mechanics, even seemingly empty space is a bubbling cauldron of activity. Pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence from the vacuum, existing for an infinitesimally short time, and then annihilating each other, returning to the void from which they came. This happens everywhere, all the time, all around us, but their fleeting existence and immediate annihilation mean they don't have observable effects in everyday circumstances. Now, consider what happens when this quantum vacuum is situated near the extreme gravitational pull of a black hole's event horizon. The intense gravity can, in a sense, tear apart these fleeting virtual particle-antiparticle pairs before they have a chance to annihilate. Imagine a pair of virtual particles appearing right at the edge of the event horizon. One of the particles, perhaps the antiparticle, might fall into the black hole. The other particle, however, the original particle, can escape into the wider universe. From the perspective of an observer far away, it appears that the black hole has emitted a particle. But where did the energy for this escaped particle come from? It couldn't have come from nowhere. The laws of physics are, after all, remarkably consistent. The crucial insight here is that the particle that fell into the black hole carried away negative energy relative to the outside universe. This negative energy effectively reduces the total mass energy of the black hole. So, the escaping particle is real. It carries positive energy away, and the black hole itself loses a tiny amount of its mass. This is the essence of Hawking radiation, a slow, steady leakage of energy and mass from the black hole, driven by quantum fluctuations at its event horizon. It's as if the black hole is slowly exhaling, shedding its very substance into the cosmos. The temperature of this radiation is incredibly low for typical stellar mass black holes. It's so low, in fact, that it's far colder than the cosmic microwave background radiation, the faint afterglow of the Big Bang. This means that, for most black holes we know of, they are actually absorbing more energy from their surroundings than they are emitting through Hawking radiation, and so they are growing, not shrinking. However, for hypothetical much smaller black holes, perhaps formed in the early universe, their temperature would be much higher, and their evaporation rate would be significantly faster. The smaller the black hole, the hotter it is, and the faster it radiates. This relationship is inverse. As a black hole loses mass, its temperature increases, and its rate of radiation accelerates, leading to a final, dramatic burst of energy as it completely disappears. This slow, cosmic exhalation is the universe's gentle way of reclaiming even the most formidable of its creations. This subtle quantum process is the universe's slow breath, a testament to the interconnectedness of space, gravity, and the fundamental nature of reality, reminding us that even the most seemingly permanent structures are subject to an eternal, gentle transformation. The event horizon is a point of no return, but not a point of no influence. Imagine, if you will, a cosmic boundary, a threshold so profoundly significant that crossing it alters not just your path, but your very destiny within the universe. This is the event horizon of a black hole. It is, in its most fundamental definition, the surface beyond which nothing, not even light, can escape the black hole's insatiable gravitational pull. It's a one-way membrane, a point of no return, a cosmic precipice. Once you've crossed this invisible line, the universe as you know it ceases to exist for you, and your fate is sealed within the singularity, a point of infinite density at the black hole's heart. This absolute nature of the event horizon has led many to perceive it as a definitive endpoint, a place where all interaction with the outside universe ceases. However, the true elegance of physics, particularly when we delve into the quantum realm, reveals a more nuanced and, dare I say, comforting reality. While it is undeniably true that nothing can escape from within the event horizon, this does not mean that the region within the event horizon has no influence on the universe outside. The key to understanding this subtle but profound distinction lies in the very nature of gravity and the delicate dance of quantum mechanics. Think of gravity not just as a force that pulls, but as a curvature in the fabric of spacetime itself. A black hole, with its immense mass concentrated into an infinitesimally small point, creates an extraordinarily deep well in this fabric. The event horizon is simply the point where this curvature becomes so extreme that all paths within it lead inwards. However, the presence of this massive object, and the extreme warping of spacetime it causes, extends its influence far beyond the event horizon. Gravitational waves, ripples in spacetime caused by massive accelerating objects, can propagate outwards from the vicinity of a black hole, even if they originate from interactions near its event horizon. These waves carry information about the black hole's mass, spin, and even its presence, influencing the orbits of distant stars and galaxies. Furthermore, the theoretical framework of Hawking radiation, which we will explore more deeply, demonstrates that black holes are not entirely isolated entities. This radiation, a slow leakage of energy from the black hole, originates from quantum effects occurring at the very edge of the event horizon. While the particles that form this radiation appear to be born just outside the horizon, their existence and subsequent escape are intrinsically linked to the extreme gravitational conditions at the horizon. This means that even as matter and energy fall into the black hole, and the horizon acts as a barrier to escape, the black hole itself is not inert. It is a dynamic entity, subtly interacting with the quantum vacuum and through gravitational influence with the broader cosmos. The black hole's immense gravity dictates the paths of objects in its vicinity, shaping the cosmic landscape around it. Stars orbit black holes. Gas clouds are drawn into accretion disks that glow with unimaginable heat, and even the very structure of galaxies can be influenced by the presence of supermassive black holes at their centers. This gravitational influence is a constant, pervasive force that extends far beyond the point of no return. So, while the event horizon marks a boundary for anything falling in the black hole's presence, its immense gravitational field, and the quantum phenomena occurring at its edge, all exert a continuous, albeit often subtle, influence on the universe beyond. The boundary is absolute for escape, but the entity it defines is not entirely cut off from the cosmic conversation. The event horizon is an absolute boundary for egress, but the cosmic symphony plays on, touched by the silent, profound presence of the abyss. Quantum mechanics allows for virtual particles to pop into existence. In the quiet hum of the universe, far from the grand, sweeping curves of spacetime that define black holes, lies a realm of profound strangeness and subtle activity, quantum mechanics. This is the bedrock of reality at its smallest scales, a domain where intuition often falters and the familiar rules of cause and effect seem to bend. Here, in the vast, seemingly empty expanse of space, a continuous energetic dance is taking place, a fleeting creation and annihilation that, while imperceptible to our senses, shapes the very fabric of existence. At the heart of this cosmic ballet are what physicists call virtual particles. Now, the term virtual might suggest something unreal, something purely theoretical. But in the context of quantum mechanics, it describes a state of being that is both temporary and, in its consequences, very real. These virtual particles are not like the stable, persistent particles we encounter in our everyday lives, such as electrons or protons. Instead, they are fleeting excitations of quantum fields. Imagine the universe as being filled with invisible, energetic fields, like an ocean of potential. Quantum mechanics tells us that even in the vacuum, in what we perceive as empty space, these fields are not truly still. They are constantly fluctuating, a subtle tremor of energy that causes pairs of particles and antiparticles to spontaneously arise. Think of it as a momentary ripple on the surface of that cosmic ocean. These particles, a particle and its antimatter counterpart, appear out of nowhere, exist for an infinitesimal fraction of a second, and then, just as quickly, they annihilate each other, their energy returning to the field, leaving no trace. This process is governed by Heisenberg's uncertainty principle, a fundamental tenet of quantum mechanics. The principle states that there are certain pairs of physical properties, like energy and time, that cannot be known with perfect accuracy simultaneously. Specifically, the more precisely you know the energy of a system, the less precisely you can know the duration over which that energy exists, and vice versa. This inherent fuzziness in nature allows for these brief violations of energy conservation. For a very short period of time, energy can be borrowed from the vacuum to create these particle-antiparticle pairs. The shorter the lifespan of the virtual particles, the larger the amount of energy that can be borrowed. It's a cosmic loan, repaid almost instantaneously. These virtual particles are not directly observable in the same way as real particles because they exist for such short durations and travel such minuscule distances before annihilating. They are, in essence, intermediaries, carrying forces and mediating interactions between real particles. For instance, the electromagnetic force, the force that holds atoms together and governs light, is mediated by virtual photons. When two electrons repel each other, it's because they are exchanging virtual photons. So while they are virtual in their ephemeral existence, their role in the universe is profoundly significant, enabling the very interactions that define matter and energy. They are the silent, tireless workers of the quantum realm, constantly bringing into and taking out of existence, ensuring that the universe is a dynamic and interconnected place, even in its deepest silences. These fleeting guests born from the void remind us that even stillness is a form of vibrant, energetic motion. These virtual particles briefly exist before annihilating each other. Imagine the very fabric of spacetime, not as a smooth, empty canvas, but as a roiling, bubbling sea of energy. Even in the vacuum of space, where it seems nothing exists, there is a constant, fleeting dance of creation and destruction happening at the quantum level. This is the realm of virtual particles. They are not like the particles we typically think of, like electrons or photons, which have a definite existence for a measurable time. Instead, virtual particles are transient phenomena, popping into existence from the quantum vacuum and then almost immediately disappearing, annihilating each other. They are a direct consequence of the Heisenberg uncertainty principle, which states that we cannot know both the precise position and the precise momentum of a particle simultaneously. This inherent uncertainty allows for energy to be borrowed from the vacuum for incredibly short periods, enough to spontaneously create pairs of particles and antiparticles. These pairs, such as an electron and a positron, or a photon and its antiphoton, are created with opposite properties. They exist for an infinitesimally small fraction of a second, a duration so brief that they are undetectable by conventional means. Their existence is inferred from their effects on the behavior of real particles. They are like fleeting ghosts, appearing and vanishing in the blink of an eye, their brief presence subtly influencing the quantum world around them. This constant flux of virtual particles is a fundamental aspect of quantum field theory, suggesting that even empty space is a dynamic and active place, teeming with ephemeral activity. They are the universe's fleeting whispers, a constant reminder of the inherent uncertainty and dynamism at the deepest levels of reality. Even in the apparent stillness, existence is a fleeting whisper, a dance of becoming and unbecoming. In the extreme gravity near a black hole, they can be separated. Imagine, if you will, the very edge of a black hole, the precipice of the event horizon. It is a place of unimaginable forces, where the fabric of spacetime itself is stretched and warped to its absolute limit. Here, in this cosmic crucible, the delicate dance of quantum mechanics takes on a new and profound drama. We've spoken of virtual particles, those fleeting entities that wink into and out of existence in the vacuum of space. Normally, they appear in pairs, a particle and its antiparticle, and almost instantly annihilate each other, their brief existence canceling out. It's a fundamental aspect of the quantum vacuum, a constant, subtle hum of potentiality. But near a black hole, this ordinary cosmic background noise is amplified, distorted, and fundamentally altered by the immense gravitational pull. The very spacetime is so curved, so intensely energetic, that it can wrench these nascent particle-antiparticle pairs apart before they have a chance to annihilate. Think of it like a powerful tide pulling two pebbles on a shore in opposite directions, one being dragged out to sea, the other left stranded on the sand. One member of the virtual pair, perhaps the particle, might be drawn across the event horizon, destined to fall into the black hole's insatiable maw. The other, its antiparticle counterpart, might be flung outwards, escaping the black hole's grip. This separation is the crucial first step in a process that will eventually lead to the black hole's demise. It's a moment where the quantum world, usually so subtle and hidden, asserts itself in the most dramatic of cosmic arenas, turning the void itself into a factory for escaping energy. The black hole, in its very act of creation and existence, becomes the catalyst for its own eventual undoing, all thanks to the exquisite sensitivity of quantum laws to the extreme curvature of spacetime. This separation, this cosmic tug-of-war at the event horizon, is not just a theoretical curiosity. It is the very genesis of Hawking radiation, the slow, steady leakage of energy that will, over unimaginable eons, cause the black hole to fade away. It is a testament to the interconnectedness of all things, where even the most powerful gravitational entities are subject to the subtle, persistent influence of the quantum realm. The black hole's gravity, rather than being a perfect prison, becomes a force that, paradoxically, allows for escape. At the brink of ultimate darkness, even the void can give birth to light. One particle might fall into the black hole, the other escapes. Imagine, for a moment, the very edge of a black hole, the boundary we call the event horizon. It's a place where the rules of our everyday experience begin to warp and bend in truly extraordinary ways. Now, recall those fleeting, virtual particles we mentioned, pairs of matter and antimatter that spontaneously appear and vanish in the vacuum of space, a constant hum of quantum activity. Near a black hole, this delicate dance of creation and annihilation is dramatically influenced by the immense gravitational pull. The intense gravity can act like a cosmic sculptor, separating these fleeting pairs. As a virtual particle pair emerges right at the threshold of the event horizon, there's a chance that one of the particles, let's say the antimatter particle, is caught by the black hole's gravity and pulled across that boundary, disappearing forever into the singularity. The other particle, the matter particle, is left behind, Because its partner is now gone, it can no longer annihilate and simply vanish. Instead, it escapes outward, carrying with it a tiny amount of energy. This escaping particle is what we observe as Hawking radiation. It's as if the black hole, in its relentless pull, has inadvertently allowed a sliver of itself, a whisper of its essence, to drift away. This is not a violent expulsion, but a subtle, constant leakage, a testament to the deep interconnectedness of quantum mechanics and gravity. The black hole isn't actively ejecting anything. Rather, the extreme conditions at its edge are forcing a fundamental quantum process to yield an observable outcome. This process is incredibly slow for massive black holes, so slow that it's almost imperceptible over cosmic timescales. But it is happening, a continuous, subtle release. The energy that the escaping particle carries away originates from the black hole's gravitational field itself. In essence, the black hole is losing a minuscule amount of its mass energy with each escaping particle. This is a profound idea, that even the most seemingly immutable objects in the universe are subject to a slow, inexorable process of change, a cosmic shedding. The separation of these virtual particles at the event horizon is the key mechanism, a delicate quantum tug-of-war where gravity plays the decisive role in determining the fate of each ephemeral partner. It's a beautiful illustration of how the vacuum of space is not truly empty, but a roiling sea of potentiality, and how even the most extreme gravitational environments can reveal the subtle workings of the universe at its most fundamental level. The escaping particle, a lonely survivor of a quantum pair, represents a tiny fraction of the black hole's immense energy, a silent emissary from the abyss. This is not a process of destruction in the conventional sense, but a slow, fundamental transformation, a gradual release of energy back into the cosmos. The black hole, in its very existence, is facilitating this ongoing exchange, a constant, albeit imperceptible, interaction with the surrounding spacetime. The energy carried away by the escaping particle is equivalent to a tiny portion of the black hole's mass, as described by Einstein's famous equation E equals mc2. So, with every escaping Hawking radiation particle, the black hole becomes infinitesimally smaller, a slow, patient journey towards eventual dissipation. This gentle leakage is a crucial piece of the puzzle in understanding the true nature of black holes, revealing them not as eternal prisons, but as dynamic entities subject to the subtle laws of quantum physics. The very act of a particle falling in causes its partner to be born into the wider universe, a cosmic quid pro quo at the edge of oblivion. And so the universe breathes, even at the edge of the void, releasing whispers of energy that paint a picture of slow, inevitable change. The escaping particle carries away energy, effectively stealing from the black hole. Imagine, if you will, the very edge of a black hole's influence, a place known as the event horizon. It's a boundary, not a wall, a point of no return for anything that crosses it. But here, at this precipice, the universe plays its most subtle and profound games, governed by the curious rules of quantum mechanics. Even in the seemingly empty vacuum of space, energy is not truly static. It flickers and dances, a constant, ephemeral creation and annihilation of particles. These are what we call virtual particles. They appear in pairs, a particle and its antiparticle, born from the quantum foam for an infinitesimally brief moment, only to disappear as quickly as they arrived, annihilating each other in a silent, cosmic blink. This constant churn, this energetic ballet, is a fundamental aspect of reality, even in the most extreme environments. Now, consider what happens when this quantum dance unfolds precisely at the edge of a black hole's immense gravitational pull, at the event horizon. The intense warping of spacetime here can, in a very specific and delicate way, disrupt the usual fate of these virtual particle pairs. Instead of annihilating each other, the extreme gravitational gradient can wrench them apart. One member of the pair, by sheer chance and the cosmic dice roll of quantum mechanics, might fall across the event horizon and be forever lost to the black hole's interior. But its partner, the other virtual particle, might find itself nudged just enough, given a tiny push away from the abyss. This escaping particle, now no longer destined for annihilation, can drift away into the vastness of space. And here lies the profound implication. This escaping particle, though it originated from the quantum fluctuations near the black hole, is no longer bound to the black hole's destiny. It carries with it a tiny amount of energy. Where did this energy come from? It didn't appear from nowhere. That would violate the fundamental laws of physics. Instead, this energy is, in a very real sense, borrowed from the black hole itself. The black hole, by allowing one particle to fall in and the other to escape, has effectively paid a price. It has lost a minuscule portion of its mass energy. This process, repeated over unfathomable stretches of time, is the very essence of Hawking radiation, a slow, imperceptible leak of the black hole's being back into the universe. It is as if the black hole, the ultimate devourer, is itself being slowly consumed, not by an external force, but by the very quantum nature of existence at its own boundary. The escaping particle, a ghost of possibility, becomes the universe's gentle reminder that even the most absolute of cosmic entities are subject to its subtlest laws. And so, the universe whispers its secrets, even from the edge of oblivion. This stolen energy is what we call Hawking radiation. Imagine this delicate dance of creation and annihilation happening at the very edge of the black hole's influence, at its event horizon. These fleeting pairs of particles, a particle and its antiparticle, are born from the quantum vacuum, a state that is not truly empty but seething with potential. Normally, they would exist for an infinitesimal fraction of a second before finding each other and canceling out, their existence leaving no lasting trace, returning their borrowed energy back to the void from which they came. But near a black hole, the gravitational pull is so immense, so overwhelmingly powerful, that it can rip these ephemeral partners apart. One particle, perhaps the antiparticle, is drawn inexorably towards the black hole, crossing the event horizon and disappearing forever into the singularity. The other particle, however, is flung away, escaping the black hole's grasp. Now, this might seem like a simple cosmic coincidence, but from the perspective of the black hole itself, something profound has happened. The particle that fell in carried with it a certain amount of energy, a negative energy in a specific quantum interpretation, effectively reducing the black hole's mass. The particle that escaped, on the other hand, is a real particle, carrying away positive energy. This outflow of energy, this gentle stream of particles escaping from the vicinity of the black hole, is what Stephen Hawking mathematically predicted and what we now understand as Hawking radiation. It's not a beam of light or a forceful emission, but a subtle thermal leakage, a whisper of warmth emanating from an object that we once thought to be utterly cold and inert. This radiation is the black hole's way of slowly, imperceptibly, releasing its energy and consequently its mass back into the universe. It is the universe's subtle way of healing, of rebalancing, a testament to the interconnectedness of all things, even the most extreme. And so, the universe's most enigmatic objects are not silent, but softly singing their own gradual dissolution into the vastness. Black holes are not truly black, but possess a faint thermal glow. Imagine, for a moment, the deepest void you can conceive, a place where light itself cannot escape, a cosmic abyss that swallows all. For decades, This was our primary understanding of black holes, perfectly black, utterly silent entities in the grand tapestry of the universe. Yet, as our understanding of the universe deepens, so too does our appreciation for its subtle, unexpected nuances. The notion that a black hole, by definition, is a region of space-time where gravity is so strong that nothing, not even light, can escape, might lead one to believe they are the ultimate in darkness, the absolute absence of emission. However, through the lens of quantum mechanics, a surprising revelation emerges. It is here, at the very boundary of the impossible, that the universe whispers its secrets. Stephen Hawking, through his groundbreaking theoretical work, proposed that black holes are not entirely devoid of energy or radiation. Instead, they are thought to emit a faint, almost imperceptible thermal glow, a phenomenon now known as Hawking radiation. This radiation arises from quantum fluctuations occurring at the event horizon, the boundary beyond which escape is impossible. Even in the seemingly empty vacuum of space, pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence and then annihilating each other almost instantaneously. These fleeting entities exist for an infinitesimally short period, borrowing energy from the vacuum and then returning it. However, near the immense gravitational pull of a black hole's event horizon, something extraordinary can happen. If these virtual particle pairs are created precisely at the edge, one particle might fall into the black hole while its partner escapes into the vastness of space. The particle that falls in can be thought of as having negative energy relative to an observer far away, while the escaping particle carries away positive energy. This escaping particle, now no longer an ephemeral virtual entity but a real particle, carries away energy from the black hole itself. This continuous process over eons means that the black hole is slowly, infinitesimally, losing mass and energy. This emission of energy, this subtle radiation, is what gives black holes their theoretical thermal glow. The temperature associated with this glow is incredibly low for typical stellar mass black holes, far below the background radiation of the universe, making it practically undetectable with current technology. Yet the theoretical implication is profound. Black holes are not eternal prisons of darkness, but are, in fact, slowly radiating away their existence. This concept challenges our intuitive understanding of these cosmic behemoths, revealing a universe far more complex and dynamic than initially perceived. A universe where even the darkest corners hold the potential for subtle, energetic whispers. It's a testament to the universe's ability to surprise us, demonstrating that even in the face of absolute gravitational dominance, the fundamental laws of quantum physics can orchestrate a slow, persistent release of energy, a faint, cosmic warmth emanating from the heart of darkness. This radiation is not a beacon, not a blaze, but a whisper, a gentle exhalation from an object that was once thought to be the ultimate silence. And so, the deepest shadows of the cosmos are not truly silent, but hum with a faint, thermal echo of existence. The temperature of a black hole is inversely proportional to its mass. Imagine, if you will, the universe as a vast cosmic orchestra, where gravity plays a powerful, resonant note. For decades, we understood black holes as the ultimate silence within this symphony, regions so dense that nothing, not even light, could escape their gravitational embrace. They were seen as unchanging entities, eternal prisons in the fabric of space-time. But Stephen Hawking, with his brilliant mind, dared to listen closer, to perceive the faintest whispers where others heard only silence. He proposed that black holes are not entirely black, but possess a subtle warmth, a temperature, much like any other object in the universe. This temperature, however, behaves in a way that is profoundly counterintuitive. It is inversely proportional to their mass. This means that the more massive a black hole is, the asterisk colder it is. Conversely, a less massive black hole is asterisk hotter asterisk. Let's unpack this remarkable idea. To understand this, we must revisit the concept of Hawking radiation, the process by which black holes are thought to slowly lose mass and energy. This radiation arises from quantum effects near the event horizon. In the chaotic quantum vacuum, particle-antiparticle pairs, known as virtual particles, are constantly popping into and out of existence. Normally, these pairs annihilate each other almost instantaneously. However, near the intense gravitational pull of a black hole's event horizon, this delicate balance can be disrupted. Imagine a pair of virtual particles appearing right at the edge of the black hole. One particle might fall into the black hole, while the other escapes into the vastness of space. To an outside observer, it appears as though the black hole has emitted a particle. Now here's where the temperature and mass relationship becomes crucial. For a particle to escape, it must carry away energy. Where does this energy come from? It comes from the black hole itself. When a virtual particle falls into the black hole, its antiparticle escapes, and this escaping particle carries away a tiny bit of the black hole's mass energy. This process, over immense timescales, is what causes a black hole to evaporate. The rate at which this happens is directly related to the black hole's temperature. The Stefan-Boltzmann law, a fundamental principle in thermodynamics, describes the relationship between the temperature of an object and the energy it radiates. For any object with a temperature, the hotter it is, the more energy it emits. Hawking's groundbreaking insight was to apply a similar thermodynamic principle to black holes, linking their temperature to the rate at which they emit Hawking radiation. So, why is a more massive black hole colder? Think of it like a very large, very dense object that is still trying to radiate heat. A larger mass means a larger event horizon, and a less intense gravitational gradient at the horizon. The quantum fluctuations that lead to Hawking radiation are less likely to result in a net energy loss for the black hole when its gravitational pull is less extreme relative to the quantum vacuum. Conversely, a smaller black hole with its more compact event horizon and steeper gravitational gradient experiences more pronounced quantum fluctuations. These fluctuations are more effective at separating particle-antiparticle pairs, leading to a higher rate of energy emission, and thus, a higher temperature. Consider a stellar mass black hole, formed from the collapse of a star. Its mass might be several times that of our Sun. Its Hawking temperature is incredibly low, far colder than the cosmic microwave background radiation. It would take vastly longer than the current age of the universe for such a black hole to evaporate through Hawking radiation. Now, imagine a hypothetical much smaller black hole, perhaps formed in the early universe. If it were significantly less massive, its temperature would be much higher, and its evaporation rate would be correspondingly faster. This inverse relationship is a beautiful testament to the interconnectedness of seemingly disparate physical laws. The concept of black hole temperature is not just an abstract theoretical curiosity. It is a bridge between two monumental pillars of modern physics: Einstein's general theory of relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of the universe at its smallest scales. Hawking's work demonstrated that these two theories, often seen as incompatible, can be unified in profound and unexpected ways. The temperature of a black hole is a direct consequence of this unification, a subtle yet powerful reminder that the universe operates on principles that often defy our everyday intuition. It suggests that even the most seemingly inert and powerful objects in the cosmos are engaged in a slow, perpetual dance of energy exchange. The temperature of a black hole, a measure of its subtle thermal glow, is a cosmic secret whispered in the language of quantum mechanics, revealing that even in the deepest gravitational wells, the universe is never truly still. Smaller black holes are hotter and evaporate faster. This might seem counterintuitive at first glance, as we often associate larger with more intense. However, in the realm of Hawking radiation, the relationship between a black hole's mass and its temperature is inverse. Think of it like a tiny ember versus a massive bonfire. The tiny ember, with its smaller amount of stored energy relative to its surface area, can radiate its heat away more quickly and thus appears hotter in its rate of energy loss. A black hole operates on a similar, albeit far more complex, principle. The temperature of a black hole is directly proportional to the strength of its gravitational pull at its event horizon. This strength, in turn, is inversely proportional to its mass. So, a black hole with a smaller mass has a weaker gravitational field at its event horizon, which paradoxically means it has a higher temperature and radiates energy at a faster rate. This is because the quantum fluctuations near the event horizon, which give rise to Hawking radiation, are more pronounced and energetic in a less gravitationally dominated environment. Imagine the event horizon as a delicate membrane. For a larger black hole, this membrane is incredibly strong, resisting the energetic dance of virtual particles. But for a smaller black hole, the membrane is thinner, more yielding, allowing these particles to be more easily separated, with one escaping and carrying away a bit of the black hole's essence. This accelerated loss of energy means that smaller black holes are, in a sense, burning through their mass at a much quicker pace than their colossal counterparts. They are like fleeting candles in the cosmic dark, their light diminishing with astonishing speed compared to the slow, majestic burn of a galactic-sized furnace. The very properties that make them less massive also make them more susceptible to the universe's subtle, inexorable processes of decay. This inverse relationship is a fundamental aspect of Hawking's theory, revealing a universe where size does not always equate to longevity, and where even the most massive objects are subject to the gentle, persistent force of evaporation. The smaller the cosmic giant, the faster it truly glows, and the sooner it will fade from existence, a testament to the dynamic and interconnected nature of all things, from the infinitely small to the unimaginably vast. The universe breathes them into being and gently breathes them out again, a cycle of cosmic effervescence. Larger black holes are colder and evaporate incredibly slowly. Imagine the temperature of an object. We associate it with the energetic jostling of its constituent particles. Hot objects have particles zipping around with great vigor, while cold objects have particles moving with less intensity. This intuitive understanding, deeply ingrained in our daily lives, also applies in a most surprising way to black holes. When we speak of a black hole's temperature, we are referring to the temperature of the Hawking radiation it emits. And just as a larger object generally retains heat for longer, a more massive black hole, in a sense, is colder and therefore radiates less intensely. The relationship is a precise one. The temperature of a black hole is inversely proportional to its mass. This means that a black hole with the mass of our Sun would have a temperature of mere billionths of a Kelvin above absolute zero. For the supermassive black holes found at the centers of galaxies, objects millions or even billions of times more massive than our Sun, their temperatures are so infinitesimally small that they are effectively indistinguishable from the cosmic microwave background radiation that bathes the entire universe. This extreme coldness directly dictates the rate of evaporation. Since Hawking radiation is a process of emitting particles, a colder object, by definition, emits less energy. Therefore, the more massive a black hole, the slower it radiates and the slower it evaporates. The timescale for such evaporation is staggeringly long. For a black hole with the mass of our Sun, it would take an estimated 10 to the power of 67 years to completely disappear. To put that into perspective, the current age of the universe is a mere 13.8 billion years, which is approximately 10 to the power of 10 years. The evaporation of a stellar-mass black hole is a process so slow that it is practically frozen in time from our human perspective. For supermassive black holes, the timescales are even more unfathomable, stretching to 10 to the power of 100 years or more. These colossal cosmic entities are, for all intents and purposes, eternal on human and even cosmic scales, their influence and existence stretching far beyond our current comprehension of time. The universe itself will likely have undergone profound transformations. Stars will have long since faded, and galaxies will have merged and dispersed before these giants even begin to noticeably shrink. This slow, almost imperceptible decay is a testament to the immense gravitational forces at play and the delicate balance of quantum processes near their event horizons. It is a process that whispers of endurance, of a patient existence that far outlasts the fleeting moments of stars and planets. The immense weight of a black hole anchors it in a deep, cosmic cold, allowing its slow exhale to stretch across eons. The concept of black hole temperature is a profound connection between gravity and thermodynamics. Imagine the universe as a vast, intricate tapestry woven from the threads of fundamental laws. For centuries, these laws seem to operate in separate realms: gravity, governing the grand dance of celestial bodies, and thermodynamics, describing the flow of heat and energy in more familiar, everyday systems. Stephen Hawking, with his brilliant mind and gentle persistence, revealed a breathtaking intersection, a place where these seemingly disparate domains meet and converse. It's a concept so elegant, so surprising, it feels like uncovering a hidden secret of the cosmos. To understand this, let's first revisit the idea of temperature. In our everyday experience, temperature is a measure of the average kinetic energy of particles within a substance, how much they are jiggling and vibrating. The hotter something is, the more its constituent particles are in motion. This is a concept deeply rooted in statistical mechanics, a branch of physics that deals with the collective behavior of a vast number of particles. Now consider a black hole. Classically, a black hole is defined by its event horizon, the boundary beyond which nothing, not even light, can escape. It's often envisioned as a perfectly black object, absorbing everything that crosses its threshold and emitting nothing. This classical view, based on Einstein's theory of general relativity, paints a picture of an object that exists outside the realm of thermal physics. However, when we introduce the principles of quantum mechanics, the physics of the very small, into the extreme environment near a black hole, a remarkable transformation occurs. As we touched upon with Hawking radiation, quantum fluctuations near the event horizon can lead to the creation of particle-antiparticle pairs. These pairs, born from the vacuum energy, would typically annihilate each other almost instantly. But near a black hole, the intense gravitational gradient can pull these pairs apart. One particle, perhaps with negative energy relative to an outside observer, falls into the black hole, while its partner, carrying positive energy, escapes. This escaping particle is what we perceive as Hawking radiation. And here's where the profound connection emerges. This emission of radiation implies that the black hole is not simply a passive absorber, but an object that possesses a thermal spectrum, much like any other hot object in the universe. The energy carried away by the escaping particles originates from the black hole's mass energy, causing the black hole to slowly lose mass. This loss of mass, this continuous emission of radiation, is precisely what we associate with a body at a certain temperature. The temperature of a black hole, as calculated by Hawking, is inversely proportional to its mass. This means that larger black holes are colder, and smaller black holes are hotter. A black hole with the mass of our Sun would have a temperature so incredibly low, far colder than the cosmic microwave background radiation, that detecting its Hawking radiation would be practically impossible with current technology. Conversely, a hypothetical microscopic black hole, if it existed, would be exceedingly hot and would evaporate very rapidly. This is not just a theoretical curiosity. It represents a deep unification of ideas. It bridges the macroscopic world of gravity and spacetime, described by general relativity, with the microscopic world of quantum mechanics and thermodynamics. It suggests that the very fabric of spacetime, under the extreme conditions of a black hole, exhibits thermal properties. It's as if the universe is whispering a secret, a reminder that seemingly distinct physical phenomena are, in fact, deeply interconnected, part of a grander, unified cosmic symphony. The temperature of a black hole is the universe's gentle way of reminding us that even in the most extreme darkness, the laws of heat and energy still hold sway, weaving a thread of warmth into the cold vacuum of space. Stephen Hawking's work unified general relativity and quantum mechanics in a remarkable way. Imagine for a moment the grandest theories of our universe. On one hand, we have Einstein's general relativity, a majestic framework describing gravity not as a force, but as the curvature of spacetime itself. It paints a picture of massive objects warping the very fabric of existence, guiding the dance of planets, stars, and galaxies. This theory excels in the realm of the very large, the cosmic ballet of celestial bodies. It's about the smooth, continuous flow of spacetime, a beautiful, predictable geometry. On the other hand, we have quantum mechanics, the realm of the incredibly small. Here, the universe behaves in ways that often defy our everyday intuition. Particles exist in probabilities, not certainties, and can be in multiple places at once. It's a world of discrete packets of energy, of uncertainty, and of fundamental randomness. Quantum mechanics governs the behavior of atoms, subatomic particles, and the very forces that hold matter together. For decades, these two pillars of modern physics, while incredibly successful in their own domains, seemed fundamentally incompatible. General relativity described a smooth, deterministic universe, while quantum mechanics embraced inherent randomness and discreteness. Trying to apply both simultaneously to extreme situations, like the singularity at the center of a black hole or the very beginning of the universe, led to mathematical breakdowns, to infinities that made no physical sense. It was as if we had two profoundly accurate maps of reality, but they couldn't be overlaid without tearing. Stephen Hawking, with his characteristic blend of intellectual audacity and relentless persistence, embarked on the monumental task of bridging this chasm. He didn't shy away from the most challenging theoretical frontiers. He sought to understand how quantum effects might manifest in the gravitational fields described by general relativity. His groundbreaking insights came not from trying to force one theory into the other's language, but by finding a subtle, elegant way for them to speak to each other. His crucial realization was that the quantum vacuum, that seemingly empty space teeming with ephemeral virtual particles, is not truly empty. Even in the absence of matter, quantum fluctuations are constantly occurring, and when these fluctuations happen near the intense gravitational pull of a black hole, near the very edge of spacetime's curvature, something extraordinary can occur. This is where the magic of Hawking radiation begins. By applying the principles of quantum field theory in the curved spacetime around a black hole, Hawking showed that particle-antiparticle pairs, constantly popping into and out of existence, could be separated by the black hole's event horizon. One particle might fall in, its negative energy effectively reducing the black hole's mass, while its partner, carrying positive energy, escapes. This escaping particle is what we perceive as Hawking radiation. This was a revolutionary concept. It meant that black holes, previously thought to be perfect absorbers from which nothing could escape, were not entirely black. They were, in fact, radiating, albeit incredibly faintly for most black holes. More profoundly, it demonstrated that quantum mechanics could have observable effects on the large-scale structure of spacetime, a feat that had eluded physicists for generations. It was a profound reconciliation, a whisper of quantum uncertainty in the heart of gravitational certainty. Hawking's work provided the first concrete steps towards a unified theory of everything, a theory that could describe all the fundamental forces and particles in the universe under a single, coherent framework. It was a testament to the power of human intellect to perceive the hidden connections that bind the cosmos. And in this delicate dance between the infinitely small and the infinitely vast, a new understanding of existence begins to softly unfold. This radiation is so faint for stellar mass black holes that it's undetectable. The concept of Hawking radiation, while profoundly elegant, describes a phenomenon so subtle for the black holes we typically observe that it remains beyond our current technological grasp. Imagine trying to hear a whisper in the middle of a roaring thunderstorm. That's the scale of the challenge. Stellar mass black holes, those born from the collapse of massive stars and possessing masses many times that of our Sun, are incredibly large and consequently incredibly cold. The temperature of a black hole, as predicted by Hawking's theory, is inversely proportional to its mass. This means the more massive the black hole, the lower its temperature, and the less Hawking radiation it emits. For a black hole with the mass of our Sun, its temperature would be a minuscule fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation that bathes the entire universe. To put this into perspective, the rate at which such a black hole would lose mass through Hawking radiation is staggeringly slow. It would take an unfathomably long time, vastly exceeding the current age of the universe, for a stellar mass black hole to evaporate completely. To detect this radiation, we would need instruments of unimaginable sensitivity, capable of discerning an infinitesimally small energy signature against the backdrop of countless other cosmic signals. Even the most powerful telescopes we possess today, designed to capture the faintest glimmers of light from the farthest reaches of space, are simply not equipped to measure this incredibly weak thermal emission. It's not that the radiation isn't there. It's just that the universe, in its grand design, has made these cosmic behemoths into almost perfect, silent observers for an unimaginably long stretch of time. The physics is sound, the theory is beautiful, but the practical observation of this fundamental process for the black holes we know best remains a distant dream, a testament to the immense scales and subtle forces at play in the cosmos. The sheer energy output from a stellar mass black hole due to Hawking radiation is dwarfed by the energy it absorbs from its surroundings, like a tiny candle flame next to a supernova. This faint whisper of evaporation is lost in the cosmic roar, a secret the universe holds close for the most massive of its dark giants. The theoretical prediction is clear, but the observational reality for these colossal objects is one of near-perfect, undetectable stillness. Even the grandest celestial bodies can hold their secrets in the quietest of emanations. It would take far longer than the current age of the universe for a solar mass black hole to evaporate. Imagine the vastness of cosmic time. We speak of billions of years, of epochs stretching beyond our immediate comprehension. Now, consider a black hole with a mass equivalent to our own sun. The process of Hawking radiation, this gentle leakage of energy, is incredibly slow for such an object. To truly grasp the timescale, we must delve into the mathematics, a language that reveals the universe's profound patience. The rate at which a black hole evaporates is inversely proportional to its mass. This means that the more massive an object, the slower it radiates away its energy. For a solar mass black hole, the temperature is extraordinarily low, a mere fraction of a Kelvin above absolute zero. This minuscule temperature dictates an equally minuscule rate of energy emission. The calculation reveals a time scale that is staggering. We're talking about numbers with 60 or more zeros. To put it into perspective, the current age of the universe is approximately 13.8 billion years, which is roughly 4.3 x 10^17 seconds. A solar mass black hole would take on the order of 1067 years to evaporate. This number is so immense that it dwarfs any human conception of time. It is a duration so long that the very stars we see would have long since burned out. Galaxies would have merged and reformed countless times, and the universe itself would be a vastly different place. The atoms that currently constitute our bodies, our planet, and our sun would have long since decayed and reformed into entirely new configurations, perhaps even new fundamental particles. This immense timescale highlights the stability of these colossal objects on human and even cosmic scales within our current epoch. While the theory of Hawking radiation dictates their eventual demise, for black holes of stellar mass, this demise is a symphony played out over a duration so vast that it effectively renders them eternal from our present vantage point. The universe, in its grandest designs, operates on cycles and timescales that invite a deep sense of perspective, reminding us of the fleeting nature of our own existence against the backdrop of cosmic endurance. And so, the sun-sized abyss, though destined to fade, will endure through an eternity that cradles our briefest dreams. Primordial black holes, if they exist, could be evaporating now. The universe, in its earliest moments, was a crucible of unimaginable density and energy. During this primordial epoch, far more chaotic and energetic than anything we experience today, it is theorized that conditions might have been ripe for the formation of black holes that were not born from the collapse of stars. These hypothetical entities are known as primordial black holes. Unlike the stellar mass black holes we observe, which are formed from the gravitational collapse of massive stars at the end of their lives, primordial black holes could have formed from the direct collapse of overdense regions in the extremely dense plasma of the early universe. Their masses could span a vast range, from incredibly tiny, perhaps even smaller than an atom, to quite substantial. It is these smaller primordial black holes that are of particular interest when we consider evaporation. According to Hawking radiation, all black holes lose mass and energy over time, but the rate at which they do so is dependent on their mass. Smaller objects have a higher temperature and radiate energy more intensely. For a black hole with the mass of a large mountain, for instance, the rate of Hawking radiation would be significant enough that it could have already evaporated entirely by the present day, some 13.8 billion years after the Big Bang. For even smaller primordial black holes, their evaporation would have occurred much earlier in the universe's history, perhaps even within the first fractions of a second. The theoretical signature of such an event would be a burst of high-energy particles, a cosmic fizzle that would leave no trace of the black hole itself. The search for evidence of primordial black holes is an ongoing quest in astrophysics. Scientists look for the characteristic radiation signatures that their evaporation might produce, or for gravitational lensing effects that could indicate their presence. If detected, it would not only confirm the existence of these exotic objects, but also provide invaluable insights into the physics of the very early universe, a time when our current understanding of physics is stretched to its limits. The possibility that these ancient, tiny remnants of the universe's infancy are now vanishing, contributing their last whispers of energy back into the cosmos, is a profound thought. It paints a picture of a universe that is not only vast and ancient, but also a place of constant transformation, where even the most extreme phenomena eventually yield to the passage of time and the subtle, persistent forces of nature. These hypothetical evaporating entities are like cosmic fireflies, blinking into existence and then fading away, leaving behind only the memory of their fleeting presence in the grand tapestry of space-time. Their potential evaporation now is a testament to the dynamic and evolving nature of the cosmos, a universe that is always in flux, always changing, and always, in its own quiet way, releasing its stored energies back into the void. The very idea that these entities, formed in the chaotic genesis of existence, might be reaching their final moments of energetic release, a gradual fading into the background hum of the universe, is a deeply philosophical one. It speaks to the impermanence of even the most seemingly robust structures in the universe, a reminder that all things, from the grandest galaxies to the smallest theoretical particles, are subject to the inexorable march of time and the fundamental laws of physics. The universe, in its infinite complexity, continues to reveal its secrets, and the potential evaporation of primordial black holes is one of those tantalizing glimpses into its deepest workings. Even the most ancient whispers of creation may now be returning to the cosmic silence. The process of evaporation is a slow cosmic exhale. Imagine for a moment the immense scale of a black hole. We've spoken of its event horizon, that boundary beyond which nothing, not even light, can escape its gravitational embrace. Yet, the universe, in its infinite ingenuity, has devised a way for even these seemingly immutable cosmic entities to, in a sense, recede. This is the essence of Hawking radiation, a process so subtle, so profound, that it paints a picture of black holes not as eternal prisons, but as entities that, over unfathomable stretches of time, can indeed cease to be. The exhale we speak of is not a sudden expulsion, but a gradual, almost imperceptible release of energy. Think of it like the gentle fading of a distant star, or the slow erosion of a mountain by the wind, but on a scale that dwarfs our everyday comprehension. This radiation, as we've touched upon, arises from the quantum fluctuations near the event horizon. Pairs of virtual particles, one with positive energy and one with negative energy, constantly flicker into and out of existence in the vacuum of space. Normally, they annihilate each other almost immediately, but near a black hole, the intense gravitational gradient can pull these pairs apart. If the negative energy particle falls into the black hole, the positive energy particle can escape, carrying away a tiny bit of the black hole's mass energy. This escaping particle is what we perceive as Hawking radiation. This process is extraordinarily slow for stellar mass black holes. For a black hole with the mass of our Sun, the rate of radiation is so minuscule that it would take far longer than the current age of the universe, trillions upon trillions of years, for it to evaporate completely. The temperature of such a black hole would be incredibly low, far colder than the cosmic microwave background radiation that bathes the universe. It is only as a black hole loses mass and shrinks that the rate of Hawking radiation begins to increase. This is because the surface area of the event horizon decreases, meaning the quantum effects become more concentrated. Imagine a snowball rolling down a hill. As it gathers speed, it also gathers more snow, accelerating its descent. Similarly, as a black hole shrinks, its radiation output grows, and it evaporates faster and faster. This accelerating evaporation is a key aspect of its eventual demise. The energy radiated away is precisely the energy that was contributing to the black hole's mass. So, with each escaping particle, the black hole becomes infinitesimally smaller, and its temperature rises, leading to more radiation and a more rapid decrease in mass. This feedback loop continues until, theoretically, the black hole completely dissipates. The final moments, as this process accelerates, are predicted to be a dramatic burst of energy, a final, energetic sigh as the black hole returns its accumulated mass energy to the cosmos. It's a testament to the universe's inherent dynamism, a reminder that even the most seemingly permanent structures are, in the grand cosmic narrative, subject to change and eventual transformation. This gradual dissipation, this slow release of energy, is a fundamental aspect of the black hole's life cycle, a quiet, yet powerful demonstration of the universe's ongoing processes. And so, the immense gravity that once held everything captive, now slowly, gently, surrenders its hold, becoming one with the vast, whispering expanse. As a black hole loses mass, its event horizon shrinks. Imagine a cosmic drain pulling everything towards its center. This is, in essence, what we often visualize when thinking about a black hole. And for a long time, the prevailing thought was that once something crossed that invisible threshold, the event horizon, it was gone forever, contributing to an ever-growing, ever more inescapable gravitational pull. But the beautiful complexity revealed by Hawking radiation paints a far more dynamic picture. Hawking radiation, as we've explored, is the subtle, yet profound process by which a black hole can actually lose mass. This isn't a violent shedding of material, but rather a gentle, quantum leakage of energy. And as this energy, in the form of particles, escapes into the cosmos, the black hole itself diminishes. Think of it like a very, very slow leak from a vast reservoir. The water level, representing the black hole's mass, gradually decreases. This decrease in mass has a direct and predictable consequence on the size of its event horizon. The event horizon, that boundary beyond which escape is impossible, is directly proportional to the black hole's mass. So, as the mass decreases, the event horizon must, by necessity, shrink. It's a fundamental consequence of the laws of gravity as described by Einstein's general relativity. The larger the mass, the greater the gravitational influence, and the further out that point of no return extends. Conversely, as that influence weakens due to mass loss, the boundary of no return draws closer to the singularity at the heart of the black hole. This shrinking isn't a rapid event for most black holes we know of. For a black hole with the mass of our Sun, the rate of evaporation is so infinitesimally slow that it would take an unimaginably vast amount of time for its event horizon to even begin to noticeably recede. We're talking timescales that dwarf the current age of the universe by many, many orders of magnitude. However, for hypothetical much smaller primordial black holes, or as a black hole approaches the very end of its existence, this shrinking becomes more significant. The process accelerates, creating a fascinating feedback loop where the smaller it gets, the faster it evaporates, and the faster its event horizon retreats. It's a beautiful dance of cosmic physics, a testament to the universe's tendency towards equilibrium, even in its most extreme manifestations. The shrinking event horizon is the black hole's slow surrender to the vastness of space-time. The rate of Hawking radiation increases as the black hole gets smaller. This might seem counterintuitive at first glance. We often associate smaller things with less power, less influence. Yet, in the peculiar quantum realm surrounding black holes, the opposite holds true. Remember, the temperature of a black hole is inversely proportional to its mass. A larger black hole with its vast gravitational pull spread over a greater expanse is colder. Conversely, a smaller black hole, more compact and concentrated, is hotter. And just as with any hot object, the rate at which it emits radiation is directly related to its temperature. So, as a black hole steadily loses mass through Hawking radiation, it becomes smaller, its temperature rises, and consequently the rate at which it emits more Hawking radiation accelerates. It's a self-reinforcing cycle, a cosmic feedback loop. Imagine a snowball rolling down a hill. At first, it picks up a little snow, growing slightly. But as it grows, its surface area increases, allowing it to gather even more snow with each revolution, and its speed increases, leading to an ever faster rate of growth and descent. The black hole's evaporation is similar, though on a vastly grander and more subtle scale. This accelerating emission means that the final moments of a black hole's existence are not a slow fade, but a dramatic crescendo of energy release. While the evaporation of a stellar mass black hole is so slow it's practically imperceptible over cosmic timescales, a hypothetical, very small primordial black hole would evaporate much more quickly, and its final moments would be a spectacular, energetic event. This relationship between size, temperature, and radiation rate is a fundamental principle of thermodynamics, elegantly manifested even in the most extreme gravitational environments. It underscores the interconnectedness of seemingly disparate physical laws, showing how the quantum world and the realm of gravity are not separate entities, but intimately linked aspects of a single, unified reality. The universe, in its vastness, often reveals its most profound truths in the most unexpected places, and the accelerating demise of a black hole is one such astonishing revelation. It's a testament to the dynamic nature of existence, where even the most seemingly permanent structures are subject to the inexorable flow of cosmic processes, a slow dance of creation and dissolution playing out across eons. The closer it gets to its end, the more eager it becomes to reach it, a final, brilliant exhalation. This leads to a runaway effect in the final moments of evaporation. As a black hole continues to shed mass through Hawking radiation, a fascinating shift occurs. Remember, the temperature of a black hole is inversely proportional to its mass. This means that as the black hole loses mass, its temperature actually increases. This might seem counterintuitive, like a fire getting colder as it burns fuel, but in the realm of black holes, it's a fundamental consequence of their nature. So as the black hole shrinks, it gets hotter, and a hotter object radiates energy more intensely. This creates a feedback loop, a positive feedback loop, where the loss of mass leads to an increase in temperature, which in turn leads to an even faster loss of mass. Imagine a snowball rolling down a hill, picking up speed and size. In this case, it's a black hole losing mass but gaining speed in its evaporation. The rate of Hawking radiation, which is already incredibly slow for stellar mass black holes, begins to accelerate dramatically. This acceleration is not a gentle, gradual process, but rather a sharpening, a quickening as the black hole approaches its ultimate demise. The very fabric of space-time around it, warped and pulled by its immense gravity, is now being energized by this increasingly intense outward flow of particles. This runaway effect means that the final stages of a black hole's existence are compressed into a relatively short period, cosmically speaking, compared to the eons it may have existed previously. It's a final, energetic gasp from an object that has dominated its surroundings for so long. The energy that was once held captive within its gravitational embrace is now being released with increasing ferocity, a testament to the dynamic and ever-changing nature of the cosmos. The once impenetrable barrier of the event horizon is dissolving, and the energy that sustained it is now fueling its own destruction. This acceleration is a key feature of the evaporation process, transforming a slow, almost imperceptible fade into a rapid, energetic conclusion. It's a moment where the slow, majestic dance of cosmic evolution culminates in a final, fiery flourish. And in this final acceleration, the black hole's long silence gives way to its last, radiant song. The very end of a black hole's life is a burst of energy. Imagine, if you will, a black hole that has been slowly, imperceptibly, shedding its mass over eons. This isn't a sudden event, but the culmination of a process that began the moment it formed. As it loses more and more of its substance through Hawking radiation, its temperature, as we've discussed, rises. This is counterintuitive, of course, because we associate hotter with more energetic, and a black hole losing mass is, by definition, losing energy. However, the temperature of a black hole is inversely proportional to its mass. So, as the mass decreases, the temperature increases. This means the rate at which it emits Hawking radiation also increases. It's a feedback loop, a gentle acceleration that builds over unimaginable timescales. For most black holes, especially those born from stars, this acceleration is so incredibly slow that it's practically imperceptible within the lifespan of the universe. A stellar mass black hole would take vastly longer than the current age of the cosmos to evaporate. But if we consider hypothetical, very small primordial black holes that might have formed in the early universe, their evaporation could be occurring now. As the black hole shrinks, its event horizon, that boundary beyond which nothing can escape, also shrinks. The intensity of the gravitational field at its surface increases, and consequently, the quantum fluctuations that give rise to Hawking radiation become more violent. The particles being emitted carry away more and more energy, and the black hole shrinks ever faster. This escalating process continues until, in its final moments, the black hole is emitting radiation at an extraordinary rate. It's like a candle burning down, where the flame flickers more wildly and brightly as the wax dwindles. The energy that has been locked away within the black hole, the very essence of its gravitational pull, is finally being released back into the universe. This final burst is theorized to be incredibly energetic, a brief but intense flash of high-energy particles and radiation, perhaps in the form of gamma rays. It's the ultimate cosmic exhalation, a final, powerful testament to the dynamic interplay between gravity and quantum mechanics, a moment when the immense density of a collapsed star is utterly undone. This isn't a violent explosion in the conventional sense, like a supernova, but rather a rapid, self-consuming dissipation of its entire existence. The energy that once held matter captive is unleashed, not in a single, instantaneous bang, but in a crescendo of increasing intensity that culminates in the black hole's complete disappearance. It is the universe reclaiming its constituent parts, a fundamental reset for one of its most enigmatic entities. The very fabric of space-time, warped and distorted for so long, finally relaxes, releasing its stored potential in a fleeting, brilliant display. And in that final, brilliant flash, the black hole's entire existence returns to the fundamental energies from which it arose, a fleeting echo in the vast quiet. This final burst is theorized to be a flash of gamma rays. As a black hole approaches the end of its incredibly long life, its evaporation process accelerates. Imagine a pot of water slowly simmering for eons. As the water level drops, the heat applied to the remaining water becomes more concentrated, and it begins to boil more vigorously. Similarly, as a black hole loses mass through Hawking radiation, its temperature increases, and the rate at which it emits this radiation also increases. This escalating emission means it loses mass faster and faster. This feedback loop, this cosmic acceleration, culminates in a spectacular, albeit theoretical, final act. When a black hole has dwindled to an infinitesimally small size, its energy density becomes immense. The quantum fluctuations at its vanishing event horizon become so powerful that the black hole effectively explodes. This explosive release of energy is predicted to manifest as a powerful burst of high-energy photons, specifically gamma rays. Gamma rays are the most energetic form of electromagnetic radiation in the universe, far more energetic than visible light or X-rays. This final flash would be the last whisper of the black hole's existence, a brilliant, fleeting effervescence before it completely disappears, leaving behind only the residual energy that has permeated the surrounding space. It's a moment of cosmic punctuation, a final, emphatic statement from an entity that has shaped the universe for unfathomable durations. The energy released in this final burst would be directly related to the black hole's original mass. Smaller primordial black holes, if they existed and evaporated, would have released their energy much earlier in the universe's history, potentially contributing to the background radiation. Larger, stellar mass black holes, however, would take vastly longer to reach this final, energetic demise. The theory of this final burst is a testament to the intricate interplay between gravity and quantum mechanics, where the most profound forces in the cosmos conspire to bring even the most seemingly eternal objects to a close. It's a reminder that even in the darkest, most powerful entities, there is a finite existence, a journey from formation to a final, radiant dissolution. This theoretical gamma-ray flash is the grand finale, the ultimate consequence of a black hole's slow, inexorable dance with quantum uncertainty. And in its final, fleeting breath, the darkness ignites, painting the cosmos with a momentary, radiant farewell. The information paradox questions what happens to the information that falls into a black hole. Imagine a book filled with stories, knowledge, and unique arrangements of words. Now, imagine that book falling into a black hole. According to the classical understanding of black holes, once something crosses the event horizon, it is lost forever, its properties indistinguishable from any other object that might have fallen in. This leads to a profound problem, known as the information paradox. This paradox arises from the apparent conflict between two fundamental pillars of modern physics: Einstein's theory of general relativity, which describes gravity and black holes, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. Quantum mechanics dictates that information can never be truly destroyed. It can only be transformed or scrambled. If a book, or anything else, falls into a black hole and is then completely erased from existence, it violates this fundamental quantum principle. This would imply that the universe is not deterministic at its deepest level, a notion that many physicists find deeply unsettling. Stephen Hawking's groundbreaking work on Hawking radiation, the slow evaporation of black holes, only deepened this paradox. Hawking initially proposed that this radiation was purely thermal, meaning it carried no information about what fell into the black hole. If the black hole eventually evaporates entirely, leaving behind only this thermal radiation, then all the information about the book, its contents, and its unique atomic structure would have vanished from the universe. This would be a cosmic bookkeeping error of the highest order, a violation of the very laws that seem to govern reality. Physicists have proposed various ingenious solutions to this paradox, each with its own set of implications. Some suggest that the information is somehow imprinted on the Hawking radiation, perhaps in subtle correlations that are incredibly difficult to detect. Others propose that the information might be stored in a remnant, a tiny, stable object left behind after the black hole has mostly evaporated, or perhaps it is encoded on the event horizon itself, a cosmic hard drive. Another idea, the firewall hypothesis, suggests that crossing the event horizon might be a more violent and information-destroying process than previously thought, creating a firewall of high-energy particles that incinerates anything falling in. The holographic principle offers another perspective, suggesting that the information content of a volume of space can be represented by a theory on its boundary, like a 3D image projected from a 2D surface. In this view, the information about what falls into a black hole might be encoded on the event horizon, the boundary of the black hole. The ongoing debate and exploration of the information paradox highlight the limits of our current understanding and the profound mysteries that still lie at the heart of gravity and quantum mechanics, pushing us to seek a more complete and unified theory of the universe. The universe remembers, even when the path of what is lost seems to vanish into the deepest night. Hawking radiation suggests information might be slowly released, albeit scrambled. This particular aspect of Hawking radiation, the potential for information to escape, touches upon one of the most perplexing puzzles in modern astrophysics, the black hole information paradox. For a long time, a core tenet of physics, specifically general relativity, suggested that once something crosses the event horizon of a black hole, it is irrevocably lost. The information about its state, its composition, its structure, its very essence would be consumed by the singularity at the black hole's center, effectively ceasing to exist in any accessible form. This seemed to contradict another fundamental principle of quantum mechanics, which states that information cannot be truly destroyed. It can only be transformed or hidden. This conflict, this apparent violation of a bedrock law of the universe, was a deep source of unease for physicists. Stephen Hawking's groundbreaking work on Hawking radiation introduced a new possibility. If black holes are not entirely black, if they are slowly emitting particles and energy, then perhaps the information contained within them is not entirely lost either. The Hawking radiation, though incredibly dilute and seemingly random, might carry subtle correlations, tiny imprints of the matter and energy that fell into the black hole. Imagine a book being burned. The physical book is gone, but the information it contained, the story, the words, is not truly destroyed. It's transformed into heat and ash. And in principle, if we could meticulously analyze every single atom of smoke and ash, we might in theory reconstruct the original book. Hawking radiation offers a similar, albeit far more complex, cosmic analog. The escaping particles, as they emerge from the vicinity of the event horizon, are not entirely independent of the black hole's history. They are subtly influenced by the quantum state of the black hole itself, which in turn is shaped by everything that has ever fallen into it. However, the process of this information being released is not a neat restoration. The scrambling part is crucial. The information is not returned in an easily readable format. It's thought to be so thoroughly mixed and encoded within the Hawking radiation that deciphering it would be an astronomically difficult, perhaps even practically impossible, task. It's like taking a perfectly organized library and throwing all the books into a cosmic shredder, then scattering the confetti across the entire universe. The original words are still technically present in the shredded pieces, but their order and context are lost, making reconstruction an immense challenge. This idea, that information might be preserved even if scrambled, offers a potential resolution to the paradox, suggesting that the laws of physics remain consistent across the vast scales of cosmic phenomena. It hints that the universe, in its deepest workings, is fundamentally a system of information processing, where nothing is ever truly erased, only transformed into a new, perhaps less comprehensible, form. This subtle whisper of preservation, even in the face of such immense gravitational forces, speaks to the intricate and interconnected nature of reality, a cosmic tapestry where even the most extreme events might not signify an absolute end. And in this slow, scattered release, the universe whispers that even what is lost may, in some form, endure. This paradox remains one of the deepest mysteries in physics. The information paradox, a concept born from the theoretical implications of Hawking radiation, presents a profound challenge to our understanding of the universe. It asks a simple yet incredibly complex question. What happens to the information contained within matter that falls into a black hole? According to classical general relativity, once something crosses the event horizon, it is lost forever, its unique properties seemingly erased from existence. This aligns with the intuitive, albeit chilling, idea of a black hole as a cosmic graveyard, an ultimate destination from which no information can escape. However, the principles of quantum mechanics, which govern the very small, state that information can never truly be destroyed. It can be transformed, scrambled, or spread out, but its fundamental essence is conserved. This fundamental conflict between the laws of gravity and quantum mechanics, as applied to black holes, is the heart of the information paradox. Stephen Hawking's initial calculations suggested that Hawking radiation, the faint thermal glow emitted by black holes, is purely thermal. This means it carries only information about the black hole's mass, charge, and angular momentum, much like the heat radiating from a simple object. If this is true, then as a black hole evaporates entirely through Hawking radiation, all the specific information about the objects that fell into it, the unique arrangement of atoms, the quantum states of particles, the very history of that matter, would be irrevocably lost. This violation of quantum mechanics' principle of unitarity, the idea that the evolution of a quantum system is always reversible and that information is conserved, is what makes the paradox so deeply unsettling to physicists. Over the decades, various theoretical proposals have emerged to resolve this paradox. Some suggest that information might be subtly encoded within the Hawking radiation itself, perhaps in correlations that are incredibly difficult to detect. Others propose that information might be stored in remnants left behind after the black hole has completely evaporated, or even that it is somehow transferred to other universes. More recent ideas, such as the holographic principle, suggest that the information about the contents of a black hole might be encoded on its event horizon, like a hologram projected onto a lower dimensional surface, and then slowly released as the horizon shrinks. Yet, despite these fascinating avenues of research, a universally accepted and experimentally verifiable solution remains elusive. The information paradox forces us to confront the very limits of our current physical theories, pushing us to seek a more complete and unified description of reality, one that can reconcile the immense scale of gravity with the delicate dance of quantum mechanics, and in doing so, understand the ultimate fate of all that enters the void. Just as a whispered secret can linger in the silence, the universe holds onto the echoes of what has been. The ultimate fate of a black hole is a gradual return to the fabric of spacetime. Imagine, if you will, the immense gravitational pull of a black hole, a point where spacetime itself is so intensely warped that nothing, not even light, can escape. For a long time it was thought that once matter crossed the event horizon, it was lost forever, a permanent addition to this cosmic enigma. However, through the lens of quantum mechanics and the profound insights of Stephen Hawking, we understand that black holes are not truly eternal. They are, in fact, slowly but surely fading away. This process, as we've touched upon, is driven by Hawking radiation. It's a subtle, incredibly slow leakage of energy from the black hole's vicinity. Think of it like a cosmic sigh, a gentle exhalation of particles that carry away a minuscule amount of the black hole's mass. This loss of mass means the black hole shrinks, however infinitesimally. As it shrinks, its temperature, paradoxically, increases and the rate of Hawking radiation accelerates. This isn't a sudden collapse, but rather a prolonged, drawn-out process that can take vastly longer than the current age of the universe for even moderately sized black holes. For a black hole with the mass of our Sun, the evaporation process would take an unimaginable 1067 years. For the supermassive black holes at the centers of galaxies, the timescales are even more colossal, stretching into the realm of 10,100 years and beyond. These are numbers so vast they defy our everyday comprehension, numbers that highlight the sheer resilience and enduring nature of these cosmic giants, even as they are destined to dissipate. The event horizon, that boundary of no return, will gradually recede. The intense curvature of spacetime will lessen. The singularity, the hypothetical point of infinite density at the heart of the black hole, will eventually be exposed, though what that truly means remains a subject of deep theoretical investigation. Some theories suggest that as the black hole nears its end, its final moments might be a spectacular burst of energy, a flash of gamma rays as the last vestiges of its mass are converted into radiation. This final hurrah, while energetic, is still a dissipation, a scattering of energy back into the cosmos. It's not an explosion in the traditional sense, but rather the complete disintegration of the gravitational well. The fabric of spacetime, which was so violently distorted by the black hole's presence, will eventually smooth out, returning to a state more akin to the surrounding universe. The energy that once formed the black hole will be dispersed, becoming part of the cosmic background radiation, indistinguishable from the myriad other energies that permeate the universe. It's a process of cosmic recycling, a testament to the conservation of energy and the dynamic nature of the universe. Even the most seemingly permanent structures in the cosmos are subject to change, to a slow, inevitable transformation. The black hole, in its eventual dissipation, is not destroyed but rather reabsorbed, its essence returned to the universal tapestry from which it arose. And so, the colossal gravity that once held dominion over its corner of the cosmos will finally yield, allowing the very fabric of existence to reclaim what was once held so tightly. Black holes are not eternal voids, but transient cosmic phenomena. Imagine, if you will, the vast, silent canvas of the cosmos. We often picture black holes as eternal, unchanging entities, cosmic monsters that simply exist, devouring all that dares approach. This is a powerful, almost comforting image of permanence in a universe that often feels fleeting. However, the elegant dance of physics, particularly quantum mechanics and the profound insights of Stephen Hawking, paints a different, and perhaps even more wondrous picture. Black holes, in their most fundamental nature, are not forever. They are not static monuments to gravity's ultimate triumph. Instead, they are dynamic, evolving objects, engaged in a slow, deliberate, and ultimately finite journey through space-time. This transience arises from a phenomenon so subtle, yet so revolutionary, that it fundamentally alters our understanding of these enigmatic celestial bodies, Hawking radiation. As we've begun to explore, Hawking radiation is the gentle, almost imperceptible leakage of energy from a black hole. It's as if the black hole is not a perfect prison, but a sieve, allowing a minuscule amount of its essence to escape over unimaginable timescales. This isn't a sudden, dramatic event, but a continuous, slow dissipation. Think of it like a mountain carved by wind and rain over eons, or a star that eventually exhausts its fuel. The process is gradual, almost imperceptible to a single observer, but over the grand sweep of cosmic history, it is profoundly significant. The rate at which a black hole emits Hawking radiation is directly tied to its mass. The more massive a black hole, the colder it is, and the slower it radiates. For the supermassive black holes that reside at the centers of galaxies, their temperature is infinitesimally low, and the rate of radiation is so minuscule that it would take vastly, unimaginably longer than the current age of the universe for them to evaporate. These giants are effectively eternal on human timescales, and even on cosmic ones. However, for smaller black holes, particularly hypothetical primordial black holes that might have formed in the early universe, the situation is different. These smaller entities are hotter and radiate more intensely. The implication of this radiation is a steady, albeit glacial, decrease in the black hole's mass. As it loses mass, its gravitational pull weakens, and its event horizon, the boundary beyond which nothing can escape, begins to shrink. This shrinking is not linear. As the black hole becomes smaller, its temperature increases and the rate of radiation accelerates. This creates a feedback loop, a cosmic acceleration towards its ultimate end. Consider the final moments of a black hole's existence. As it dwindles to an infinitesimally small size, its radiation would become incredibly intense, culminating in a final, spectacular burst of energy, perhaps in the form of gamma rays. This is not an ending of silence and oblivion, but a vibrant, albeit brief, exhalation back into the universe. It's a transformation, not a cessation. This concept challenges our deeply ingrained notions of permanence. We see the enduring stars, the seemingly unchanging void, and we infer eternal existence. But the universe, at its most fundamental level, is a realm of constant flux, of transformation, of intricate cycles. Even the most seemingly immutable objects are subject to the subtle, pervasive laws of physics. Black holes, far from being eternal prisons of spacetime, are participants in this grand cosmic ballet of creation, evolution, and eventual dissolution. They are born from the collapse of stars. They grow by accreting matter, and they will, over unfathomable stretches of time, gently fade away, their matter and energy returning to the universal tapestry. They are not voids that simply exist, but phenomena that transpire. And so, the seemingly eternal monoliths of gravity are, in truth, ephemeral entities, participating in the universe's slow, deliberate exhale. The universe is a dynamic place, even for its most extreme objects. When we gaze at the night sky, it's easy to perceive a certain stillness, a grand, unchanging tapestry of stars and nebulae. Yet beneath this serene surface, the cosmos is in a constant state of flux, a breathtaking dance of creation and transformation. Even the most seemingly immutable and powerful entities within this vast expanse, such as black holes, are not exempt from this universal dynamism. For eons, black holes were considered the ultimate cosmic prisons, singularities from which nothing, not even light, could escape. They were thought to be eternal, unchanging endpoints of stellar evolution, forever consuming matter and energy. This perception, while awe-inspiring, painted a picture of ultimate stasis at the heart of these gravitational behemoths. However, as our understanding of the universe has deepened, thanks to the brilliant insights of physicists like Stephen Hawking, this view has been profoundly reshaped. We now understand that black holes, far from being static, are engaged in a slow, yet inevitable process of change. This change is driven by the subtle, yet powerful, principles of quantum mechanics interacting with the extreme gravitational environment at the event horizon. The concept of Hawking radiation, which we've explored, reveals that black holes are not entirely black. They possess a faint, thermal glow, a whisper of energy escaping into the void. This radiation, though incredibly weak for most black holes, signifies a continuous loss of mass and energy. It means that black holes are, in fact, slowly evaporating. This evaporation is not a sudden, cataclysmic event, but a gradual, cosmic exhalation that can take unfathomable amounts of time, far exceeding the current age of the universe for stellar mass black holes. Yet, the very existence of this process underscores the universe's inherent dynamism. It demonstrates that even the most extreme manifestations of gravity are subject to the fundamental laws that govern all of existence, including the probabilistic nature of quantum fields and the thermodynamic imperative of energy exchange. The idea that a black hole, a symbol of ultimate density and gravitational power, can, over cosmic timescales, fade away and eventually cease to exist, is a testament to the universe's ceaseless transformations. It suggests that endings are not absolute but are often merely precursors to new beginnings, or simply a return to the fundamental constituents of reality. This dynamic nature extends to all cosmic phenomena. Stars are born, live their lives, and eventually die, often in spectacular supernovae, scattering the elements that will form new stars and planets. Galaxies collide and merge, reshaping their structures over billions of years. Even the fabric of spacetime itself is thought to be expanding, a grand, ongoing evolution. To contemplate the slow, inevitable evaporation of a black hole is to grasp a profound truth about the universe. Nothing is truly permanent, and change, in its myriad forms, is the only constant. This perspective can be incredibly calming. It reminds us that even the most daunting challenges, the most seemingly insurmountable obstacles, are part of a larger, dynamic process. The anxieties and stresses that weigh us down, like the immense gravity of a black hole, are not necessarily eternal. They are part of a cosmic ebb and flow, and with enough time and understanding, even the deepest wells of darkness can begin to dissipate, returning to the fundamental, ever-changing nature of existence. The universe breathes, and even its most formidable entities are but fleeting whispers in its grand, ongoing song of change. Our calm exploration has covered the fascinating concept of Hawking radiation, a gentle reminder that even the most seemingly immutable forces in the universe are in constant, subtle flux. We've journeyed through the quantum whispers near the event horizon, the improbable birth of escaping particles, and the quiet, thermal glow that signifies a black hole's slow surrender to the cosmic tide. We've seen how these behemoths, born from collapsing stars, are not eternal prisons but transient phenomena, destined to fade back into the fabric of spacetime. Tonight, we have reviewed the principles of quantum mechanics interacting with gravity, revealing a universe far more interconnected and dynamic than we might initially perceive. The idea that even a black hole, a symbol of ultimate density and inescapable gravity, can slowly evaporate, can leak energy and eventually cease to be, offers a profound perspective on impermanence and transformation. It suggests that endings are not always abrupt or absolute, but can be gradual, subtle, and even beautiful in their own quiet way. This understanding, this quiet wonder, can help us to see our own lives and challenges through a different lens. Just as the black hole's immense gravity eventually yields to the delicate dance of quantum particles, perhaps our own moments of struggle or stillness are part of a larger, unfolding process. The vastness of the cosmos, with its immense timescales and subtle mechanisms, can remind us of our own small, yet significant place within it. It can dissolve the sharp edges of our anxieties, smoothing them into the gentle, continuous flow of existence. And so, as the echoes of these cosmic revelations settle around you, Allow the gentle understanding of impermanence and transformation to wash over you. Feel the weight of your day begin to lift, replaced by the quiet awe of universal processes. The universe is a symphony of change, and you are a vital part of its serene melody. It is time to rest now. Sleep well. Good night. If you happen to still be awake, you can drift into the next chapter now, continuing this journey of quiet wonder and peaceful curiosity.